Hey everybody, happy Tuesday to you today. Um, my plan for today is to go through that free response AP question that I gave you yesterday. Hopefully you've had a chance to take a look at it. I know some of you did. One person had it turned in within an hour of me posting it, which I thought was pretty impressive. Um, but hopefully by the time you're watching this, you've had a chance to at least look at it and think about it a little bit. I will just go through this by looking at the scoring rubric, and then we will get into graphing of the polar form of equations, which I'm not sure how familiar you guys are with that, so I'll treat it as if you've never seen it before today. So this is the question on the screen that you were looking at, and I'm just going to go straight to the rubric and go through this fairly quickly. Part A said, find the position of the particle at time equals 3. Well, the graph that we were given, this is the y-coordinate of the location, and this isn't y prime, this is actually y. So the y value is just the value that we get by looking at the graph. And because we're looking at line segments, it's safe to assume that between time equals 2 and time equals 4, it's going to go halfway from -1 to 0. So -1/2 for that. And then the x-coordinate, here's that formula that we really emphasized leading up to the AP test this year. I know what the x-coordinate was at time equals 0. We were given that that was 5. And then we are given an equation for the derivative, the rate that the x value is changing, dx dt. And so this is where it was. This is how much it changes between 0 and 3. And this is absolutely something that you would just plug into your calculator. Do not try to find an antiderivative of that stuff. Plug it in your calculator. Make sure your calculator is in radian mode, and it should just spit out 14.377. So those are the coordinates. Be sure you answer the question, and that is 3 points. Part B is only worth 1 point. This is the other formula that we saw for parametrics, and that is dy dx is equal to dy dt over dx dt. Again, dy dt we just get by looking at the graph, saying the slope of a tangent line to that line segment is 1/2. And then the equation that we are given is x prime, dx dt. So plug, let's see, what value? Find the slope of a tangent line at time equals 3. So plug 3 into the x equation, the x prime equation, to get 9.956376. Notice they're using more than the 3 places after the decimal here, but then their answer is rounded to the nearest thousandth, 0.050 or 0.05. Either one is okay. Part C, the speed. Well, we've actually found up here on part B, we've found the horizontal component of the velocity and the vertical component of the velocity. So we're just going to take 9.956376 squared plus 0.5 squared, the square root of the square, or the square root of the sums of the squares of the components of the velocity. That's where that 9.969 comes from. I get 1 point for the expression, knowing that it's the square root of the sum of the squares of the components, and then 1 point for the answer. And then finally, part D, the distance that it travels is the integral of the speed function. Tricky part about this one is that even though our x prime is given over the whole interval between 0 and 4, our y component actually changes at t equals 1. So between time equals 0 and time equals 1, we see on the graph that the line segment is going down with a slope of 2, so a -2 slope there. And then for the rest of it, it stays at a constant. And so the slope of the tangent line to the graph between 1 and 2 is 0. And again, plug these into a calculator. Absolutely, positively plug them into a calculator, get those two, add them up, and that is our total distance. The first integral is the distance traveled between 0 and 1 second, and then the second integral is between 1 and 2. So there we go. Moving on to polars, and I'm not sure how much of polars you guys got to see last year in pre-calculus. So I'll start off at a very basic level and say graphing in polar coordinates is just a different way of graphing. The way you have graphed most of the graphs that you've done is in rectangular form, meaning the location is determined by a horizontal and vertical distance from the origin, your x and y coordinates. I go to the left or to the right by this amount, and then I go up or I go down by that amount. And that's the rectangular form of graphing. Polar graphing, the location of a point is determined by how far we are away from the origin, and then how much of a rotation have we undergone from the positive x-axis. And so, for example, if I say the rectangular coordinates of this point up here, we're going to count over to get from the origin to that point. We're going to go over to the right 1, 2, 3 units, and then we're going to go up, and it's a little bit tricky to see. We're going to go up 1, 2, 3, 4. And if I do both of those things, if I go to the left by 3, I'd like a dotted line here. Excuse me, I'm going to the right by 3. So from this point, sorry about this. I think I need to reset my computer. That's being awfully pokey. So from this point, we move over to the right, 1, 2, 3. And then from this point, we go up 4 to get to that point, or we go up 1, 2, 3, 4, and then go to the right by 3 to get to that point. And so the coordinates of that point, rectangular, over 4, up 3, the rectangular coordinates would be 4, 3, where it's just understood that the first one is the horizontal component and the second one is the vertical. If I say, what are the polar coordinates of this point? Instead of x and y, my polar coordinates are going to be r, which is my distance from the origin, and theta, which is the angle of rotation from the positive x-axis. So the distance from the origin, counting 1, 2, 3, 4, 5 units away from the origin. And then I'm not sure what this angle of rotation is. This would be a pi over 4. This would be a pi over 3. So we're halfway between pi over 3. Well, not even exactly halfway. We're somewhere between pi over 3 and pi over 4. I'm not sure exactly what that amount is, but I do know that if we're in rectangular coordinates, about 53 degrees. I'm just doing a conversion over into radians. It's somewhere around 0.925 or 9.93. So this is an approximate. I'll put about 0.93 radians. But that 0.93 radians, that is the angle of rotation, again, to get from the horizontal, the positive axis, that is my angle. That is my theta value of about 0.93. And again, if it's easier for you to think about, you can think of that as about 53 degrees. But those are my coordinates, r and theta, instead of x and y. And then a couple other details about this. If you have a negative r, that means whatever the angle is telling you to go, whatever direction the angle is pointing, if I have a negative r, that means we're going in the opposite direction. So if I had the same theta value, but a negative r, my point would be somewhere down here instead of up here. And also theta can be negative also. Instead of a positive rotation, we could do a negative rotation in the clockwise direction. And so just to help us visualize what a polar graph can look like, and I suppose I had one here on the first slide. If you remember anything about polar graphs, if you've seen anything about polar graphs, you remember that they can be some pretty cool looking graphs. If I use the phrase or the terms limacone and lemniscate and cardioid, the spiral of Archimedes is a fun one. There's all these different shapes that you can make. So what we're looking at right now is the graph of y equals sine of 2x. And we know what y equals sine of 2x looks like. It's a periodic function. Because of the sine of 2x instead of sine of x, we know that the period's been shortened by half. And so instead of a period of 2 pi, it's a period of just pi. And so I get a graph that looks like this. And so as x goes between 0 and 2 pi, we see this behavior. It goes up, comes down, goes up, comes down, goes up, back to 0. And so to imagine the graph of r equals sine of 2 theta, I've got to think, instead of moving to the right as we look at different values of x, I'm going to think of it as a rotation. There's a reason I've got this radar screen. I'll be thinking about, instead of moving from left to right across my screen, I'll be moving around my screen, starting with the positive x-axis. And so for a quick example, and this, I really wish that I was standing in front of you demonstrating this, because this is a demonstration that I've done over the years that works out pretty cool. What I would be doing is standing in front of the projector, holding my 2-meter stick and walking across the room in front of you, showing you that as I move across the room, we can see what this graph is doing. It starts off at 0, at the middle of my 2-meter stick, and then it goes up to 1, and then down to 0, and then down to -1, down by my feet, and then up to the middle, up to the top, probably up somewhere close to my head, then down to the middle, down to the floor again, up to the middle. And that's what it's doing. As I'm walking across the room in front of you, as the x value is changing, the graph is going up, coming down, going up, coming down, going up, rectangular mode. And then what I would do is I would say, now, instead of me moving from left to right, I would take that 2-meter stick and I would spin it in front of you. And I'm going to start with it pointing in the positive x direction. So right now, actually, this is a pain. Right now, my 0 is right at the middle. And as I rotate this, notice that, oops, sorry. As I move this up, the graph is moving up along that meter stick until it gets up to the top. And then it comes back down to the middle. Now it's at 0 again. Now over here, the graph is actually back in the negative direction. The negative part of my rectangular graph is corresponding to this pointing in the positive direction. The negative part, this loop over here, is matching up with that negative part, at least until, sorry about this, again, this is incredibly awkward as I try to do this, until I get to horizontal, and then this part of the graph again comes to 0. And then as I continue to rotate around, it's rotating, it's increasing, and I realize it's going down. It's down by the floor, but it's increasing. This is still my positive direction, the direction that the ruler is pointing. Until we get to that point, it's back at the origin, and then it goes to these negative values. As I'm rotating over here, these negative values are tracing out that part of the curve. And I realize this is very difficult to think about. I'm sure some of you are shaking your heads at your screens right now. I'm going to try to emulate this at least a little bit more by color coding. This part of this curve, where the graph starts at 0, increases, and then decreases back to 0, that on this graph is going to look like this section of the curve, where I'm rotating between 0 and pi over 2. That's the part that's getting traced. And I'm tracing twice just for emphasis. It doesn't repeat itself. It just is traced twice. And then we're back to 0, just like this graph is back to 0. And then the next section of the graph, let's stick with blue. I've got these negative values between pi over 2 and pi. And so these values between pi over 2 and pi, that's this section of the graph, but because my values are negative, my theta is pointing up into the second quadrant, but those negative values are getting traced down here in the fourth quadrant, going in that direction. And then once I get past pi, this part of the graph is back to positive values, so positive values between pi and 3 pi over 2. That's going to correspond to, let's see, now we're down in this quadrant. Whoops, I lost my pen. Not sure why that happened. Down here, because if my angle is pointing between pi over 2 and 3 pi over 2, excuse me, between pi and 3 pi over 2, now these are positive values again. So it's tracing out that loop. And then between 3 pi over 2 and 2 pi, my values on this graph are negative. So I'll switch over to, let's see if purple, nope, that's blue. Where's my purple? My negative values down here between 3 pi over 2 and 2 pi in this quadrant is where it's pointing, and so negative values show up over here on the other side. And so that would be the last part of that graph. You can graph in polar form on your calculator, but it's going to take even more time to explain how to do that. And it's not something that I'm deeming to be especially crucial for us as we do this stuff. So let's talk about translating back and forth between polar and rectangular coordinates. So first, let's go from, actually, I'm going to change my mind. Let's go from rectangular to polar. We're comfortable. If I have x and y values, how do we find r and theta? So take a look at how I got this graph labeled. X and y, vertical and horizontal, my angle of rotation, and then r is my distance to the point. So if I know what x and y are, of course, x squared plus y squared equals r squared. So if x squared plus y squared equals r squared, we could say that r is the square root of x squared plus y squared. Looks familiar. And then if I know x and y, I could say tangent of theta equals y over x, which means theta is the inverse tangent of y over x. So if I give you points that are in rectangular form and you need polar form, plug them into these formulas. If you have to go in the opposite direction, if I know what r and theta are, we'll find x and y by using some formulas that you probably learned in physics or pre-calculus when you're doing the vector section in pre-calculus last year. Sine of theta equals y over r, which means y is r times sine of theta. And similarly, cosine of theta equals x over r, which means x is r times cosine of theta. Y equals r times sine of theta, x equals r times cosine of theta. So given r and theta, we can find the x and y coordinates using these formulas. All right. So let's see. Oh man, I feel like we're getting into long video territory again. I'll have to see. It's always a mystery when I stop my video to see how many minutes. Sometimes I think it's going to be 14 and it's 34, and sometimes I think it'll be 28 and it's 12. We'll see which one it is this time. I'd like to take a look at, I'm going to make an attempt at graphing some polar graphs. So I'm going to say, what if we have a graph that looks something like this, where the value of r starts off positive and then fairly steadily decreases as theta increases. And let's put 2 pi, I'm going to put 2 pi right there. So one full rotation, r value starts off positive, and then it decreases down to 0, and then decreases to negative values. And so I've done a terrible job of making my scale. I'd like this halfway point to be pi, which means I've got pi over 2, I've got 3 pi over 2. And so let's do a little bit of connect the dots here. At theta value of 0, my r value is 1, 2, 3. So it starts off over here. And then as we rotate between 0 and pi, so one full or one half rotation, the r value is going from positive 3 down to 0. So I think what we would probably see here is it starts off a distance of 3 away. If it stayed 3, by the way, we'd have this nice circle, but it's decreasing. Still decreasing, still getting closer. As I go through a rotation, I'm almost at pi. Oops, I need to speed this up. By the time I get to a rotation of pi, I need to be back to a value of 0. Interesting. And then from this point, as my r is, or as my theta is going between pi and 2 pi, so as I'm making the rest of this rotation, the direction that my curve needs to be is now in the negative. So as I'm pointing down here to values just a little bit bigger than pi, my r values need to be somewhere back here, somewhere back in the negative values. So we'll have, let's see, I guess I'm going to think about this. At my 3/4 rotation, I'll be at a negative value, so it'll be up here. Let's see. I think we'll get a graph. It'll be somewhere down in this quadrant. By the time I make it to 3 pi over 2, it needs to be back around that same 1.5, but now it's a negative 1.5. My angle is pointing down here in the 3 pi over 2 direction, but the value of my function is a negative roughly 1.5, so it's back in this direction. And then it's going to continue to get farther and farther away until I get to a rotation of 2 pi, where it's going to be over here at negative 3. So probably something about like that. And this is by no means perfect, but a graph that looks something like that. Maybe I should do just a couple more of these. Let's do one that's even easier. Let's just do a constant r equals 2. And this is easier because that means we start at r equals 2. Our distance away from the origin stays at 2. So if I make one full rotation, even though it's kind of a lumpy circle, we'll end up with the graph that looks like a circle. And then one more. Oh, I'm not sure how crazy I should get. I don't want to get too crazy. I'm going to do one that I think is similar to one of your homework problems. And have it go up and then come and level off for a while and then decrease, something like that. And here again, I'm going to say that this is 2 pi. We'll say that right about here, where it reaches the value of 0 is pi. And let's see what something like this would look like. Starting at 0, back to 0 by the time I get to pi, but it's increasing pretty fast at the beginning, so it'll be heading out in this direction. But then as we loop around, I need to get farther away. I need to get to a distance of 3 away by the time I'm about halfway to pi. So I think it'll be somewhere up here. And then let's see, as my angle approaches pi, looks like I'm getting closer to 0 faster. So I think it'll be a little bit misshapen, something about like that. And then it'll stay there for a little while. And then as I rotate between pi and 2 pi, I've got negative values, starting off fairly slow, but then increasing. By the time I get to an angle of 2 pi, this thing needs to be over here at negative. So I think something around like that. Hopefully this is making some sense for you guys. Hopefully, go back and rewatch this. Rewatch it, pause it once in a while, and think about what's going on. But and also there's some good examples in the book for you to take a look at also. But I want to get to the last thing that we need to do, which is the slope of a tangent line to a curve. And I want to do specifically the slope of a line that is tangent to the curve, r equals 2 minus sine of theta. And I want to do it specifically at theta equals pi over 3. Notice the phrase I'm using, the slope of a tangent line to the curve. dy dx. What is dy dx when I'm given r in terms of theta? Not an x or a y to be seen. But let's go back to the translation. If I have r and theta values and I need x and y values, y is r times sine of theta, x is r times cosine of theta. And so when I'm trying to find change in y over change in x, I want the derivative of this, dy d theta over dx d theta. But because r is a function of theta, we're going to have some product rule. Now, if you were taking the AP test and this was going to be on the AP test, I would have you memorize this. As it is, you're not going to have to memorize this. It goes like this. The derivative of y in terms of theta, chain rule here, we got the derivative of the first times the second, dr d theta times sine, plus the first times the derivative of the second, r times the derivative of sine, which is cosine. And then likewise, for the derivative of x, dx d theta, I've got the derivative of r times cosine, dr d theta times cosine, plus r times the derivative of cosine. But of course, the derivative of cosine is negative sine, so it ends up being minus. So this is the formula. You don't have to memorize it. You'll just have to use it. I believe I only have one of these problems in your homework for, well, maybe obvious reasons. This is kind of a mess. This is a monster of an equation if you had to memorize it. In fact, I would probably recommend don't memorize it. Just think of it like this. You know how to translate from radians to degrees, excuse me, from radians to rectangular. And so it's just the derivative. R prime times sine plus R times the derivative of sine. Um, anyway, so there we go. So back to what I want to do. I want to find the specific one tangent to this curve at that point. And so plugging stuff into the formula. If this is R is 2 minus sine of theta, then drd theta is just negative cosine theta. Derivative of negative sine is negative cosine times sine plus, here's R times cosine. R is just the expression that we're given. And then the second part, drd theta, still negative cosine times cosine minus, there's R again, times sine of theta. So it's really not that bad. It's just a lot of stuff going on and keeping track of what's R and when R is a function and when R is just R and all that kind of stuff. But there we go. This is the slope of a tangent line for any value. So if I want to find the specific slope when theta equals, what did I say, pi over 3? We just plug it in. Plug it in here. Cosine of pi over 3 is 1/2. Plug it in for sine. Sine of pi over 3 is square root of 3 over 2. And all you have are sines and cosines of theta. So it ends up being a whole bunch of square root of 3's over 2. It ends up being a whole bunch of 1/2s. A lot of simplification. I'm not too concerned about the simplification. Man, I'll even read it off. You end up with, boy, negative 1/2 times square root of 3 over 2 plus, in parentheses, 2 minus the square root of 3 over 2, end parenthesis, times 1/2. There's your numerator, divided by negative 1/2 times 1/2 minus, in parentheses, 2 minus 3 over 2, end parentheses, times the square root of 3 over 2. It's a monster. But when you simplify and combine terms and rationalize denominators, I came up with 1 minus the square root of 3 over 4. I'm not too concerned about simplification. If you want to leave the problem in the homework in unsimplified form, I am perfectly fine with that. That said, here is your penultimate homework assignment. For many of you, for most of you, the penultimate math homework assignment in high school period. Maybe for some of you, your penultimate math homework assignment ever is these 6 problems, a little bit of graphing here, a little bit of computation. And I will put a PDF up of these specific questions from the book. Man, it was a long one. I'll make tomorrow's or Thursday's short. Okay. Hopefully you're having a great week. Hopefully this is a good one. I'll see you guys later. Bye-bye.